Hello, this is the video tutorial for the Focus Applied Technologies Combustion Analysis System. Now, the information we're going to be discussing here is in our paper manual, which you can download from the website, and contains a lot of additional information pertaining to the wiring of the system and whatnot. But what we're going to focus on right now is the software. So to start the software, you simply click on it, and you'll see that there's kind of a blank screen here because we don't have the data loaded in it yet. First, what we'll do is we'll look at the configuration, the lower left button, and then we'll load some data. So in the configuration, you'll see that most of the stuff on the left-hand side is dedicated to the engine. You want to know certain parameters of the engine for thermodynamic calculations. Like, for example, you want to know the bore and stroke, the connecting rod length. If you don't know the connecting rod length, you can assume it's about 1.7 times the stroke. That's fairly common. This is a big diesel engine, so we're using a number closer to 2. And you want to know the clearance volume. The clearance volume you can get from the compression ratio, and it will give you the compression ratio if you hover over it. Additionally, you set it up for either a 2 or 4 stroke type system. And that's all the setup you really need for the engine. There are some other parameters pertaining to your operating conditions, but those we'll see later. Okay, once the engine is set up, you probably want to go to the sensor, and we can have up to 3 sensors. The first sensor is your combustion sensor. The next sensor is either your intake or exhaust manifold sensor, or potentially turbo boost or something else like that. Each sensor is going to have its own identifier. Usually this is the model number. And it'll have a 0 voltage. Now, this is the 0 pressure gauge voltage, meaning at 0 gauge pressure, what voltage does it read? Generally, it's about, for most of our sensors, about 500 millivolts. In this case, we've put it at 520 because there's a very slight offset in this particular sensor. The sensitivity, millivolts per psi, is generally listed on the outside of the sensor, and you just type it in here. So for a different sensor in your intake or exhaust manifold, you'd put in the different parameters for that particular sensor. When we go down, we have some time-based information. So when we're operating the dynamometer without an encoder, when we're operating the combustion analysis system without an encoder, we would use these parameters here. So in this case, we're talking about 10,000 hertz and 20,000 samples. So that means it's about 2 seconds per 2 seconds per reading, with an interval of 1 second between readings. Looking down at the lower left, this is the parameters associated with the encoder. Generally, we have a 1440 pulse per revolution encoder, and we don't really know where the index is going to be initially, potentially. So one of the things we may do on the first run is we may click these to be auto, and then when we do our first run, it will set them up with whatever they actually are, and then you really don't need to set them. So that's a very convenient thing to be able to do. Finally, the last one is pulses within the index. Generally, this is set up as 4, and that allows us to read multiple channels. Okay, the last thing on here in the lower left is your number of cycles. For example, if I want to read 20 cycles, 20 revolutions of the engine, you put 20 in here. The more you read, the more memory it chews up, so typically we'd use a number of 5 or 10 or 20, something like that. There's a few things down here you'll never have to change, which is your device number and your card. Your start channel number, generally these are both set at 0 or 1 or whatever it's set at. Also, this very last line down here, DAC not found, that says I'm not connected to the hardware. The software will still run, and it works exactly the same way whether we're connected or not. In fact, it's one of the nice things about this software is we've pre-saved a bunch of raw data, and when we open the file associated with them, it will load them exactly as though we had run it for the first time on the machine. So what we did is we just pulled in some data from a run, and you notice if you looked at the title of it that it was a 1600 RPM, 100 Newton meter run. So it immediately shows us some of the analysis. The upper right is pressure as a function of crank angle. That was the upper left. The upper right is pressure versus volume. This central graph is pressure and index pulse versus either time, if we're in time base, so over on the lower left, or because we're using an encoder in this case, it's time versus crank position. You'll notice that there is an index pulse, a very high index pulse, once per revolution. You'll notice also that this is a 4-stroke engine, so we get a pressure pulse once every other revolution. So in this case, we're on the compression stroke, and over here we're on the exhaust stroke, and then the next rev, compression stroke, and then exhaust, et cetera, et cetera. You'll also notice we only have a half a cycle's worth of data, and that's because we're starting with this partial first cycle. So down here in the graph section, it says, okay, we're starting with cycle number 1, and it's only a partial cycle. So let's move it over. You can move it over by using left or right arrows, or you can slide it back and forth, or you can just type it in. So, for example, now we're on the 3rd cycle, which would be this one over here. And you can see we have a very nice pressure trace. There's a little bit of a noise out over here. You can also see that we've plotted, in this case, this orange trace. That's the compression pressure. So that's also called the motored pressure trace. Generally, the motored pressure trace starts at 1 atmosphere, and it goes up according to the geometry that you've input for the engine and the polytropic coefficient. But also we can have, in this case, the engine had a turbocharger on it, and so the intake pressure was actually slightly higher. It was about 1.3 bar in this case. So if you type in intake pressure of 1.3 bar and say refresh, you'll notice that the pressure peak increased quite a bit. Well, yeah, we've got a higher intake pressure initially, and so you can see the intake pressure is 1.3 bar. And so, of course, when we compress, it goes to higher pressure. You'll also notice that the measured pressure trace and the modeled compression pressure trace are very, very close. They need to be. If they're not, there's something wrong. Like, for example, if we had our index offset incorrect, then this is saying that our index occurs at 30 degrees. Well, let's say it occurred at 0 degrees. And if we refresh our screen, you'll notice, okay, what it's saying is that our index pulse, which is clearly happening after top dead center, it's happening at about 30 degrees after top dead center. If we were to look at this, you could clearly see this is wrong. The compression trace here needs to rise at the beginning of the measured pressure data. So what this says is, no, our index is much later, so let's give it a later number. In fact, we know it's about 30. So if we gave it a number that's too big, it would shift the curve too far the other way. Okay, so now you can see, well, our compression trace goes up before the measured pressure goes up. So clearly our index offset is too large. So we'll go somewhere in between, and we'll use 30 because we know that number is correct. And when we refresh the screen, we say, okay, now we have beautiful agreement between our compression pressure and the compression pressure measured from the actual data trace. Okay, so that's one of the first things you do is you'll verify by looking at the compression pressure, which you select from the graphic analysis. Under the graphic analysis, there's lots of different analysis you can look at. We didn't measure pressure 2 or 3 because we didn't have the sensors in there, but you can look at things like your mass fraction burn. Let's look at the mass fraction burn. And the mass fraction burn goes from 0 to 100% during combustion. There's a rapid combustion in here initially, and then a somewhat slower combustion later on. If we want to zoom in on this, we can simply select the portion of the screen we want to zoom in on. So you'd click and drag. Let me see if I can get this to work. Click, maybe right click. You click, there we go, okay. So you have to click and drag your cursor if you want to zoom in to a given portion on the screen. And now we've zoomed in, so we have a little bit better resolution in here. If you want to go back to the old scale, you can click on these boxes and it'll go back to the previous scale. Additionally, you can double click on the axes and it pulls up something that says, okay, what is my minimum and what is my maximum? So for example, I want my minimum to be 0, and then you can say save, or you can click on auto scale and you can change it to log scale or show grid lines or whatnot. Okay, so now we're back, we're set 0 to 120 bars or whatever. We have very good resolution in here. Now what I wanted to show you is we have very rapid combustion here. This is your pre-mix burning. And then we have a slower combustion later on. This is your mixing controlled combustion. Remember, we're looking at a diesel engine. And so you've got a pre-mix combustion followed by mixing controlled combustion. So to look at the mass fraction burn, let's look at the heat release rate, and we'll see very clearly the the rapid heat release here during the premix combustion, and then over here we have a lower hump that's still there, which is the mixing controlled combustion. And in this case, it's not very distinct because we're looking at an instantaneous piece of data. We're looking at cycle number 3. So there's a fair amount of noise in each cycle. Let's go to cycle number 4 and 5. And sometimes you'll see there will be cycles where you've got some inconsistency from cycle to cycle. In this case, our COV of IMEP, the coefficient of variation of IMEP, is only about 1%. That's quite stable. In other cases, like near idle, you may have surging, and so you'll have a few high peaks and low peaks and high peaks and low peaks. And we've got some data. We can look at that, and that will show up in this data here. If you want this data to look cleaner, instead of looking at the instantaneous data for, say, cycle number 6, we can look at the average data. And now it's been averaged over all the cycles. And now you can see you get a very clean, smooth curve. Of course, over here, there's no combustion. Your combustion hasn't started. Your combustion starts at 335 degrees. And after about this point, there's no combustion. And in fact, we have a blowdown section over here. So over here also, this is just noise, so you don't need to pay attention to it. The part that we're really interested in is right here in the middle. So we've got this beautiful analysis. How do we save it? Well, you can right-click in your graph and give it a name, like, for example, analysis. Maybe because I know this is 1600 and 100 Newton meters, and maybe I'll call this analysis 1 or something like this. Now what that does is it saves all of your curves that are displayed up here to a separate file, and it's very nice. You don't have to look through a lot of data. You've got it all in one file. We can do further analysis on this, but I think I'll just zoom out, look at this, and maybe I'll go back and say, well, let's look at, you can look at combustion temperature. Of course, combustion temperature, you probably want the right intake temperature over here. In this case, because it's got a compressor on it, we had a fairly elevated intake temperature, and we'll give it at 360. Also, this is our polytropic coefficient. Normally, it's about 1.2 to 1.4. You put in whatever gives you the best match. So here's our intake temperature, and if you float over it, you'll see that your intake temperature is starting out at 360, just about where we expect it to be. We have a rapid temperature rise during the premix combustion. We have slower temperature rise during mixing controlled combustion. We have a descent in the temperature during the expansion stroke, and then we have a rapid drop here. This is during the blowdown. This is when the exhaust valve is open, so you get a very rapid drop in the temperature, as you'd expect. Okay, there's just some of the analysis that we can look at. When we want to take a measurement, as I mentioned, you just click on run once, and it'll give you a set of data. If you don't like that data, just click it again. Alternatively, you can go into monitoring mode. When you click on monitoring mode, it'll continuously run and redisplay the data. Now, the thing is, if you're automatically saving, you will very quickly overload your hard drive. So we do not recommend that you do auto-saving in monitoring mode. And generally, we just recommend that you run it, you get a nice piece of data you like, and then you save it. If you're in monitoring mode and you're running and you want to stop it, then you simply click on stop and it will stop the data acquisition. The parameters shown here are the ones that are highlighted in white are numbers that you can change. How many cycles do you want to display, and which cycle do you want to start with? And then your total number of cycles, these are based on your captured data. So in this case, we captured 11. We only used 9 in our average because, remember, the first one was bad. The last one we can't see because we're only displaying 5,000 points, and if we display more points than that, it slows down Windows. So we've excluded 2 cycles from our average. And again, we saw already, here's the analysis you can do. You just click on whichever ones you want to see. And you can also tell it, oh, I want it to go on axis 1 or axis 2 if you want the y-axis to be labeled on the right or left. There's some scaling factors you can put in here, some filtering and whatnot. Now, one of the last things we want to look at is the start of injection. So our start of injection, that is the beginning when the measured pressure trace just begins to deviate from our motored pressure trace. But what if we want to look at ignition delay? If we want to look at ignition delay, what we can do is we can enter the injection angle of ignition. Now, we know down here that the start of ignition happens at 3:35. Let's say the start of injection was at, I don't know, maybe 3:15. If I put in 3:15, the difference between these two will be about 20 degrees. And so now it gives the ignition delay down here is 20 degrees. Yeah, what that says is based on the combustion that we've got and injection starting at 315 degrees, we have 20 degrees of crank angle rotation before the measured pressure trace deviates from the motored pressure trace. Okay, so that's the setup. That's how you use it. Over here also, you can see we've got the PV diagram. And if you click on this, you can go to, for example, a log scale. And we can turn it into a log scale, in which case the expansion and compression should look like straight lines. So you can see these are quite straight lines. So we've got a very nice system over here. You can see we're probably opening up our exhaust valve a little bit early, so we're getting the blow down slightly before we're getting to bottom dead center, and that's why you have this deviation from a straight line over on this side. So there's your PV diagram done in log. Of course, again, you can right-click it and save it to a file. The analysis down here, what we're looking at is the peak pressure, and of course that should agree with what we see drawn on the screen over here for the blue curve. Let's get rid of the analysis of temperature. I like to keep compression pressure on there just because it very clearly shows me that the model is matched up nicely. So if we hover over this, it should tell us that our peak pressure, in this case, is 97, so we're right about 100. So he's saying your peak pressure is 100.9, and it is occurring at 372 degrees. Well, our index is right at, our top dead center is 360. This means your peak pressure occurs about 13 degrees after TDC. Indicated mean effective pressure in bar is about 20. We've got 1% coefficient of variation in IMEP, fairly stable combustion. And our ignition delay in this case was about 20 degrees. Now, we can save this. We can save it with a new name. And you can write your description in here. So you can call it whatever you want to. And you can say, okay, this was a Cummins 1600, 100 Newton meter engine. So you can say, okay, I'm going to save this and save it with some special name. It'll put a date on here for you automatically. So if you want to accept its date timestamp, you can accept that. Otherwise, you could say, let's see, Combustion Analysis System Test Data 1 or whatever, and it'll be saved into a file you can pull into Excel. Quite easy to use. Okay, let's open another different piece of data, see if we can see some other interesting stuff. We have a lightly loaded piece of data right here. And you can see we have a much lower peak pressure. You can also see it looks like maybe our index isn't lining up very well. Let me put these back to linear scales. I like to see linear scales on these. It's a little bit clearer. And what we'll do is we'll say, okay, clearly we've got an offset in our index. And let's go check our configuration. Okay, it says it's at 30, and it's a little bit less than 30 in this case. So this must have been done earlier when the index was in a slightly different position. So maybe we'll say this is, it's certainly closer to 10 degrees or maybe even less. And we have to refresh. Okay, and that moved it over. It's really quite close on this side. Our intake pressure is right. We could adjust our polytropic coefficient, but first, we know that it's very lightly loaded, so let's look through the individual traces. Here's the second cycle, third, fourth, fifth, sixth. You can see it's pretty consistent. There's not a lot of cyclic variation. You can also see we've got a very small amount of area in this PV diagram between the expansion trace and the compression trace. That's because we're simply not burning very much. In fact, if we were to cut out injection altogether, we would expect that the measured pressure trace and the combustion pressure trace overlie one another. And that's practically what's going on here. We maybe want to move back to the right just a teeny bit to get those guys to line up perfectly. So now we're pretty much splitting hairs because the differences we're talking about are so infinitesimal. But now you can see these two guys overlay each other really quite nicely. Some of the other things we could do would be to say, well, let me change the intake pressure. In this case, I probably wasn't running 1.3 intake pressure. I was probably running probably just about 1, maybe 1.02, we'll say, a very small number. Now you can see, okay, it's looking like it's deviating a little bit. We maybe want to move the trace over to the right some more. So we say maybe it's 18 degrees or something. Let's see how that looks. And you can see beautiful agreement between our compression trace and our measured pressure trace. And so this makes us happy. We can say, okay, yeah, this is giving us good data. Now, the pressure data, that's something you actually need to measure. Normally, you would expect it to be 95% of atmospheric pressure. But in this case, because it had a turbo, where we measured it at the time, and you shouldn't have to do a lot of moving your index back and forth. If your index was creeping for some reason, okay, you can go to your configuration and move the index back and forth. Also, you can play with the polytropic coefficient. That's under your graphic analysis, and it's set up for 1.22. If we put it for 1.4, kind of a crazy high, and we refresh it, we'll see that our compression pressure is clearly too high, right? So one of the ways to get this would be to operate the engine in a motored scenario. So you get it up and running, and then you cut ignition and measure it, and then make sure that your motor trace and the measured pressure trace overlie one another perfectly. Now, in this case, that's not the case. So clearly, I put in a number that's too high. 1.4 is not the sort of number you'd expect to see on a running engine. Maybe 1.3. That'll bring the motor pressure trace down just about in agreement. And you could argue that we could move the index over just a wee bit and have this match up. Actually wouldn't be correct from the very beginning of it. So that says, okay, our polytropic coefficient is probably a little bit too high. Sorry, wrong one. So we'll put it back to maybe 1.25. And sorry, let me get this in there. 1.25, 5, and that should be about right. And again, we see very, very good correlation over here. Again, if we want to look at some of the other parameters, for example, mass fraction burn. And you see a pretty, very small amount of mass burned altogether. But, see a pretty good, pretty decent curve in there. If we want to look at XB or something else, we can go ahead. If you put too many traces on here at a time, then one of them will overwhelm the other in terms of the axis. So try not to look at too many at once, but all of this data is already saved in the data file. And so you can just go to your data file and pull it open in Excel or something like that and graph it all. It's quite easy. So that basically, we've gone through everything on the interface, and it's fairly straightforward. It should be a very easy to use system. And like I said, if you get confused, you just come back here and start and set these parameters to be automatic and do your first run, and it will set it up for you, and then you shouldn't have any difficulties with it. Apart from that, follow the paper manual, and in a worst case scenario where you just can't figure it out, then give us a call and we'll be happy to walk you through it. Okay, with that, we hope you use your combustion analysis and you get very interesting data from it. We're always interested in discussing the actual data. How did you get the data? What was the parameters you were running? What does it look like? Strange forms of combustion and stuff like that. So get some very interesting data. By all means, discuss it with us and we can help look into the analysis. Thank you very much, and good luck with your combustion analysis system.